And our philosopher, Yogi Berra, says, you can see a lot by looking, so that's what we're going to do. So now we want to look at neutrinos, high-energy neutrinos, and they're hard to detect. So we're going to try to come up with a detector for them. So in 1960, Moisey Markov, along with Bruno Pontecorvo, said, we propose to install detectors deep in a lake or in the sea and detect neutrinos producing charged particles with the help of something called Trankov radiation. So let's talk about that a little bit. Okay, so we want to detect a neutrino. You can't see a neutrino. They don't have any electric charge, okay? So the only way you can see a neutrino is when they crash headlong into a nucleus. They make a nuclear reaction, giving many charged particles that produce light. Now, neutrinos, to hit a nucleus doesn't happen very often, so they're hard to detect. Okay, so here is a little cartoon. We've got a neutrino coming in. We don't see anything. There's a big interaction. We make particles. One of them, for example, could be a muon. This muon makes light. We have an array of detectors, and we detect that light, and that's how we detect neutrinos. So the way we detect the light is using something called a photomultiplier tube. A photomultiplier tube is the inverse of a light bulb, okay? You put light in here and electricity comes out the other end, okay? So that's how you detect light in a photomultiplier. Now, this Trankov radiation is when this muon goes through ice or water, it's traveling faster than the speed of light. And so it has like a sonic boom. And it puts out radiation that we call Trankov radiation. It's light that's in the ultraviolet and blue. So it's ultraviolet and blue light that comes out. It comes out in a cone. It's just like these ducks. They have a bow wave. So that's the light is coming out in this kind of a bow wave from this particle. So this is an example. This is from a nuclear reactor spent fuel pool. So it has lots of particles coming, radioactive particles coming out of the spent fuel. They put it down in water, and you see this Trankov light. You see it glow. I've actually seen this. You can go into a reactor and look at the pool, and you see this blue light coming out. So that's Trankov radiation. Now, the problem was that water didn't work out very well for lots of reasons. And so it was decided, let's do ice. So if you want to do ice, the South Pole is where to go, obviously. 50,000-year-old ultra-pure ice instead of water, okay? So this is the South Pole. We'll talk a little bit more about it. This is the runway that the plane will land on. So this is the idea of IceCube. We want to transform a kilometer cubed, 1 kilometer by 1 kilometer by 1 kilometer, of natural Antarctic ice into a Trankov detector, okay? So we're going to have these strings that go down about 2,500 meters, all the way down almost to the bedrock, okay? And we're going to put in lots of light detectors to detect this Trankov light, and in this way we'll instrument billions of tons of ice. So this is our big detector. There's no one else who's going to build a detector this big for neutrinos. So we've got it. Here's the Eiffel Tower, by the way. Okay, so we're going to the South Pole. It turns out that the U.S. owns the South Pole.